Okay. All right. So, ladies and gentlemen, so you've all been waiting for. So, in stoichiometry, it is literally the.
Wait, we're actually doing this?
We're doing it. Yeah. So this is the unit where you look at if I have this many grams of one substance, how many grams of another substance do I need to make it react? The unit is going to end with us all making our own samples of black powder. So I got tons of stuff over there. So we're all going to make black powder, and black powder is a mixture of 3 components: sulfur, potassium nitrate, and charcoal. 1 second. And you need to get all 3 into their stoichiometric ratios. You have to have just the right grams of sulfur, just the right grams of potassium nitrate, just the right grams of charcoal. And if you do, you go poof, and it makes a big cloud of smoke. If you put that behind a metal ball, it'll shoot the metal ball out of a tube, which we're not going to do necessarily. I have a little tube over there. But if you get any of those wrong, they don't work. And that's what stoichiometry is all about. If I have this many grams of A, how many grams of B do I need to make the reaction work? Next question. Shave and a haircut, 2 bits. Okay.
Is it really true that if you play how is Minecraft related to psychometry? Stoichiometry? Yes.
Stoichiometry, excellent question. If you've played Minecraft, you know there are recipes that exist where you have this many
drugs?
Right. So like you need this many of this material and this much of this material to make one of that. And it's a recipe. Well, chemicals work in a recipe just like that. You need this much of A, this much of B to make this much of C. And we're going to revisit that towards the end of class. Now, here's the cool thing. Stoichiometry is not hard. It is almost all math, but it's not hard. And I've been peppering all of the skills you need throughout the whole year. So what can you do in stoichiometry? Well, you can compare moles of one substance to mass of that same substance. You can convert between moles and mass of the same substance. What do we use to convert between moles and grams? Exactly, the T-chart. And where do we find the conversion? On the periodic table, exactly. So we use the periodic table to convert between grams of something and moles of something. And you've been doing this since September. There are moles to grams. So you've already got that down. I'm going to teach you later on how to convert between grams of something and volume of something when you have gases using gas density. Yeah, the middle row is or the middle aisle is going to have to go because these things are so long. So they're like 4 or 5 inches longer, and we've got 4 of them. So the middle aisle is going away, and then they're getting squished. But anyway, so I'll teach you how to do that. That's go this way. Go this way. Go this way. All right. You've learned how to convert between moles and molecules because you learned Avogadro's number that tells us there are 6.02 times 10 to the 23rd molecules per mole. Please put your phones away. In every fashion, put them all away. Put all the phones away. All the phones away. I will take them next time I have to mention it. Okay. So, and then, this is what we're doing today. We're going to compare between moles of one thing and moles of another thing. And you already know where the conversion comes from. The conversion comes from the balanced chemical reaction. I have 2A, that reacts with 3B to make 4C. Or I have 2A, reacts with 1B and makes 6C. That is a mole ratio, and that's where we go from moles to moles. A little bit later, we're going to learn moles to mass, probably Tuesday of next week. And then the most important thing that we need to do so we can make all the cool chemicals we want to make and have a lot of fun is if I have this many grams of A, I'm going to do this many grams of B and this many grams of C to make the reaction work. All right. Questions? Okay, so these conversions you've already seen before. Off the periodic table, 1 mole of O2 equals 32 grams of O2, and this is a chemical. This comes from a chemical reaction. Now, one thing I need to mention, I'm going to mention numerous times, and one thing I need to mention is, in reality, you rarely get the amount of products that you calculate you should get. So, for instance, if you were to weigh all of your ingredients, you're going to make some cookies, you got your batter and your, okay, box cookies. You got your batter, your eggs, your milk, and your whatever else. So you got your batter and you weighed all the ingredients in the batter, and then you made the cookies and weighed all the cookies they made. You're going to make fewer cookies by mass than the batter, because some's going to be on the spoon, some's going to be left in the bowl, some's going to end up in the bottom of the oven, some's going to get eaten. But anyway, you always make less than you calculate you should make, and that's called percent yield. And we're going to talk about that. But that concept is important to think about, that in real life, the actual product you make is usually lower than the calculated product you make. Okay. If you are good so far, give me a thumbs up. I'm going to go slow. I'm going to talk slower when we're actually doing when I'm walking you through it.
Is it always the same amount less?
No.
It just changes randomly?
It depends on the reaction. Yeah.
Okay.
It depends on the reaction conditions.
So if a reaction happens twice, like the same reaction, would it be the same?
Yes. Okay. Ideally, yes. Okay. Shall we move on?
Yeah.
Okay. So, T-chart. You guys have done a million of these things already. So again, like I said, I'm peppering the skills in you to do stoichiometry throughout the year. So you make your tea, and what you start with goes up here. Okay, so your starting unit goes in the box, and a lot of people don't understand where to get started. They're like, what number do I start with? Well, here's the thing. A starting unit will never have another thing tied to it. It'll never be like this per this. Like grams per mole, that's 2 units. That requires 2 boxes, so it can't be the standard starting unit. Okay? Like miles per hour is miles per hour. So if you have something that's this per this, then it's not going to be a starting unit. It's usually going to be the thing that says, if we have, or if we want. That's going to be usually our starting unit. Okay? And then what goes in this box here? Nothing. Like I said, only 1 box. But then when we're on our way, we take our unit and our label and we bring it down. So we bring down our unit and our label, and we're going to convert to something else. Previously we've been going from grams to moles and moles to grams. Okay, so no difference. Like I said, remember in September I said that you could do this, and then in January, or I guess February now, you can do this, like 6 boxes. Yeah. No big deal. Okay, so you just convert. And then you bring it down again, and you convert, and you bring it down again, and you keep converting until you have the unit and the label that the exercise is asking for. So if it says how many grams, you keep doing it until you have grams of whatever it's asking for. If it says how many liters of carbon dioxide, you keep converting until you have liters of carbon dioxide. All right, how are we doing? Thumbs up if you're with me. If you have questions, wave your hand around. Okay, looks like half of you were with me, and half of you were like, I just had a big lunch and sitting in my stomach, that wet rag, I don't want to fall asleep. Yeah. Okay, 3 things in each box. Each box gets a number, a unit, and a label. 23 grams of sulfur. 38 moles of oxygen. Okay, every box gets 3 things. Please, it says every year for the last 23 years, don't shortcut your units. Write all 3 things in each box. Because if you come to me and you're like, Mr. Byers, I don't understand why I got this one wrong. I'm like, I have no idea what those numbers represent. You just got a bunch of numbers in boxes. I don't know what numbers represent because I don't know if you got the ratio upside down or not. Okay, every box needs to have a number, a unit, and a label. 36 grams plutonium. Okay? Then we just keep going. So, some important points to keep in mind. First and foremost, don't do any math until you have your goal unit and label. Okay? Don't do any math along the way. And people are going to be, they're going to be tempted to. You're going to be like, well, the ratio is 2 to 2. I'm going to make that 1 to 1. Don't do any kind of reduction or any kind of math at all along the way. 1, you could make a mistake along the way. And 2, if I don't see the work that I want to see, then no partial credit for you. So don't make any math, don't do any math at the very end. Again, don't carry down numbers, only carry down your unit and label. So you take the unit and label down, you don't take the number down. When you are done, check your math, look for division errors, and then finally, this one's a little tricky at your level of experience, but ask yourself if the number is reasonable. If you start an exercise with 36 grams, you should not end the exercise with 550,000 grams.
Absolutely.
So if you start an exercise with 36 grams and you end an exercise with 18 grams of another thing, you're probably on the right track. If you start with 0.23 grams and you end with 56,000 grams, you're probably on the wrong track. Okay. Shall we do this one together?
Yeah.
All right. So here's the exercise. We're gonna make some muffins. If a recipe requires 4 eggs for each batch of 20 muffins, how many dozens of eggs do you need to buy to make 180 muffins? And I'm gonna go slower so we can all follow along. If I go too fast, let me know. If I go too slow, bang your head on the table and know I'm going too slow. I told you about the dry erase marker situation, right?
Yeah.
So feel free to bring your own dry erase marker. You can hide it in the room if you want. Okay, so we're gonna make our T chart. Make our T chart. Okay. Nothing goes down here. Who can figure out from the exercise in the purple box what our starting thing is? What do you got?
180.
Exactly. It says we're starting with 180, and not only does it tell you our goal is to make 180 of something, it's not 180 per something. It's just 180. It doesn't have anything attached to it. So we want to make 180 muffins. What's next?
You said every box you have 3 things in it, it's only 1.
Yeah, because this is not a chemical.
Oh,
Yeah, if it was a chemical, it would be like grams of whatever.
Okay, would it be 20 muffins for like diagonal?
Okay, so we're gonna bring down muffins. Yeah, so we're gonna bring down our muffins. And the muffin thing is every 20 muffins, like Hunter said, requires 4 eggs. Now, some people like to physically cancel things out, like physically take their pen and say, all right, I got muffins, and muffins are canceled out. You can do that if you want, not required in any way, but sometimes people like to do that. Now, am I done? No, because I can't go to the grocery store and ask for 600 muffins.
Absolutely.
What I can do is I can buy dozens. Or I can't go and buy 600 eggs. I can buy dozens of eggs.
Oh.
So eggs are sold by the dozen. So I get 12 eggs for every 1 dozen of eggs. And again, if you want to cross out, you can cross out. That's fine. If you don't, that's fine too. So now, question.
Don't you move it over 1 more? Like, I thought there was another blank space.
Oh, I am out of conversions.
Okay.
So I have what I want. I have dozens of eggs, so when I go to the grocery store, I know how many dozens I need to buy.
Okay.
So now that I have the unit I want, now I do some math, and I say, all right, the numerator is 180 by 4, and the denominator is 20 by 12. And that's what you do. Once you have the unit you want, it just becomes a fraction with a bunch of numbers. No variables, just a bunch of numbers. So bang on your calculator and figure out how many dozens of eggs I need to buy at the grocery store for my muffin party.
Bridget, you guys want to do? Okay, you want to take this? Thank you. The laser.
Just please don't use your phone as a calculator. If you need a calculator, I can throw one at you, but please don't get in the habit of using your phone as a calculator.
No.
No. Oh,
Three.
tres? Three, yeah. So when I do the math, I need to buy 3 dozen eggs to make my 180 muffins.
That's alright.
So that is the basics of stoichiometry. Only thing different between now and the next 3 weeks is we're going to replace muffins with grams of sulfur, and we're going to replace eggs with grams of potassium nitrate. Yes?
So since it's dozen,
Mhm.
but we crossed out eggs. Well, okay, sure. It's just a fact.
Dozen eggs, yeah. It's the analogy we got. Okay. So the next thing is molar mass. This is on here because it's important to know what molar mass is. Molar mass is the grams from the periodic table. So this is exactly the same slide that we used way back in September to do grams and moles. Do you want to practice molar mass, or are you pretty comfortable pulling things off the periodic table? Just do one practice? Okay, so our one practice is how many moles is 89 grams of carbon dioxide? Let's do this one right here. How many grams, or how many moles is 89 grams of carbon dioxide?
Carbon dioxide.
Yes, CO2.
Wait, where'd you get that? Wait, what's 60? Oh, it's 30.
Is it 2.0?
Yeah, it is 2.02. That's what I
So,
thought.
yeah, so moving right along, we know that we need grams of CO2, and we're going to convert to moles of CO2. And the periodic table tells us that carbon is 12, and then each oxygen is 16. Are you with me so far?
Yeah.
Yes.
Okay. So 12 plus 16, usually 44. So 44 grams of CO2 is 1 mole of CO2, and the math becomes 89 over 44, which is pretty much 2.0 something. That's all. 2.0 something.
Yeah, 2.02.
2.02 moles of CO2. Okay. So if you're feeling comfortable with doing the mole gram thing, we can move on. Moving on. Okay. Limiting reactant. Okay, this is new.
Okay.
You know when you play like it's Fortnite too. Ooh, maybe I should make a new slide for Fortnite. Yeah. When you know when you play Minecraft that there's recipes. Yep. And to make so if you never play Minecraft, that's okay. Your assignment tonight is go play Minecraft. Everybody should play Minecraft. It develops your brain.
For real.
Okay, so the recipe, guys, the recipe to make an iron pickaxe is 3 iron ingots and 2 wood sticks. So if you have a pile of iron ingots and a pile of wood sticks, you know that you need at least 2 wood sticks and 3 iron ingots to make 1 iron pickaxe.
Yeah. Right.
Well, for reasons that we're not going to explain, we want to make as many iron pickaxes as possible.
We're going mining.
We're going to go mining. We need a lot of pickaxes, iron ones too. And we're going to have a pile of ingots and a pile of wood sticks. The limiting reactant is the thing that gets used up first and determines how much we can make. When we run out of one of them, we can't make any more. Does that make sense?
Yeah.
The other thing is called the excess reactant. And right now, we're going to learn about how to find the limiting reactant and how to figure out how much is in excess. You understand the word excess means extra? Yeah. All right. So consider this exercise. How many iron pickaxes can you craft with 12 iron ingots and 10 wood sticks? So the first thing we're going to do, read that. So you understand what's going on.
And then there's 2 excess wood.
Yep, exactly. You're already thinking about how to do it. You're like, I play Minecraft. I know how to do this. Let's rub a little chemistry on it. This is what we do. First thing we do is write a balanced chemical equation. And this balanced chemical equation tells me I need 3 iron ingots plus 2 wood sticks to make 1 iron pickaxe. And again, we don't need the 1, we can just leave it IP. To make 1 iron pickaxe. So can you see how this balanced chemical equation would match that recipe?
Yeah.
We're doing this tomorrow too. We're gonna turn Minecraft recipes into chemical equations.
Let's go.
Perfect.
I love Minecraft.
And I wish I could play Minecraft. It'd be like really cool, but
Do the education edition.
yeah. Well, we're going to wade into it.
They have chemistry.
Okay. So what does this mean? I need 3 iron ingots and 2 wood sticks to make a single iron pickaxe. So I ask myself, okay, let's pretend it is the iron ingots that is limited. So I have 3 iron ingots. Nothing goes right there. And the ratio says, sorry, no, not 3, 12. 12 iron ingots. Never start with a conversion. Never, ever start with a conversion. I have 12 iron ingots. And the ratio says I need 3 iron ingots to make 1 iron pickaxe. So if the ingots were limiting, how many pickaxes would I make? 4. So 12 divided by 3 is usually 4. So I would make 4 iron pickaxes if the iron ingots were limited. Well, let's ask the same thing about the wood sticks. I've got 10 wood sticks, and the ratio says for every 2 wood sticks, I'm going to make 1 iron pickaxe. So if the wood sticks were limiting, how many iron pickaxes would I make?
5.
I would make 5. So 10 divided by 2, usually 5 iron pickaxes. So this tells us that once I have made 4 iron pickaxes, I have run out of iron ingots. So the iron ingot is what's called the limiting reactant. There's only 1 T in limiting for reasons I don't know. And the wood sticks are the excess reactant. So far, so good?
Yeah.
And we are going to practice this. So now that we know which thing gets used up first, and therefore is limiting, and we know how much we made based on the limiting thing, the next question is, how much is left over? How much is in excess? And to do that, we go backwards. We take the 4 iron pickaxes that we just made, and we say, all right, this ratio says to make 1 iron pickaxe, I require 2 wood sticks. Okay, do you see what I just did?
Yeah.
To figure out how much is used up, and therefore, and then by extension, how much is left over, I start with my product and figure out how much I had to use to make my product. So I said, I'm going to make 4 iron pickaxes based on the limiting reactant of iron ingots. So how, based on my product of iron pickaxes, how much of my excess did I use? And I required 8 wood sticks out of the 10. So my excess is 2 wood sticks. Oh, there it is. Wood sticks in excess. That's limiting reactants. So you make 2 T-charts with each reactant. The thing that makes the least product is your limiting reactant. Then you use the product you made and figure out how much of your excess you had to use, do a little subtraction, and that is your excess that is remaining. All right, how are we feeling about this?
Great.
Okay. If you have any questions, wave your hand around. If you're feeling good and want to move on, give me a thumbs up.
The iron pickaxe analogy really helped. Yeah,
that actually helped me a lot.
Yeah.
That's good to know. I will try to put video games into my lessons as much as possible.
Definitely not.
I don't know how that would work with Fortnite though.
We'll figure something out.
No, we get it building, I think.
Yeah.
This is a fun conversation. I have a core memory about 10 years ago, so I've been teaching about for about 10 years. My cousin works in Silicon Valley, and like for Google and all those companies, and he was really into World of Warcraft way back then, and he's like, create an algorithm for min-maxing your dexterity and your constitution. And he's like, yeah, that would actually work. And like, imagine you have this piece of equipment, create an algorithm for min-maxing your thing. Like, people probably do that. Like, that would be great for a math exercise. You're like, World of Warcraft with math.
The way the mind works.
Limiting has one T. Like I said, anyway.
Does it really?
I'm pretty sure it does.
Yes, it does.
Yeah, it didn't catch it in that one though, which is kind of weird. Okay, so yeah, no, it's the English language. It's a short vowel, so if it's a short vowel, you use two consonants, except in limiting. And there's another one. Oh, traveling is another one. Anyway, whatever. Anyway, so you got your mole ratio. Limiting reactant is one that gets used up first, determines the amount of product made, and your excess is what is left over after the limiting is used up. Yeah. Okay, moving forward?
Yeah.
Moving forward. All right, these are for you guys. These are actually chemicals. We're going to do one together, and then the rest are for you. Okay, so first and foremost, here's our chemical reactions. First equation is this. How many moles of chlorine, there's our goal, are required to make 3.4 moles of copper 2 chloride? So how many moles of chlorine do we need to make 3.4 moles of copper chloride? So follow along with me. Question?
Doesn't it need to be like a full mole though?
Nope.
Huh?
Molecules, that's an excellent question. Molecules need to be whole numbers. Moles, because they're 6.0 times 10 to the 23rd, can be fractions or decimals. So that's an excellent question. And it's going to come up next week in the simulation. Molecules need to be whole numbers. Moles can be fractions because moles is a whole bunch. All right, so we're going to make our T-chart. I'd like to leave this one up there if that's okay. And then nothing's going to go here. And it says I need to make 3.4 moles of copper 2 chloride. Okay. Do you see why I started this way? Can you see in the back 3.4?
Yeah.
And now I'm going to move down my moles of copper chloride, moles of CuCl2, and it asks me to how many moles of chlorine. So I'm going to put moles of chlorine right up here. That's a 2. Pretend that's a 2. Try that again. There we go. And what is my chlorine to copper chloride ratio? It's 1 to 2. Based on the chemical reaction, for every 1 mole of chlorine, I'm going to need 2 moles of copper chloride. If you want to cancel out, you can. I'm not going to. I'm going to try now. So the math becomes 3.4 over 2, and our unit is whatever's left over in the upper box, moles of chlorine. 1.7?
Yeah.
So what this means is I require 1.7 moles of chlorine to make 3.4 moles of copper 2 chloride. Are you seeing it in your head?
Yes.
Questions? If you're ready to do your own, give me a thumbs up. Okay, this one's for you and Candy. Determine the moles of oxygen released by the decomposition of 5.6 moles of agua. That burning sensation you feel, that's learning. You must be Ashley.
I'm not an idiot. Come on, man. So. Okay, so you're gonna take oxygen, which is 16. Is oxygen 16? Yeah. 16 times 6. Okay, you can take that.
I don't know if I'm right.
You're gonna multiply it by.
Yeah.
Where'd you get that?
Stop.
Move your hand.
Oh.
Go back.
This is O2. That's only one mole of O2. And then this is 2 moles of
Dennis, are you working diligently?
Oh,
yeah.
Dennis
is not working.
How to make that equal?
I need you to be an,
No.
I need you to be an active participant in your own education.
Yes, sir. So that needs to be equal, which it is equal, because O2 has 2 oxygen.
Go back from where you
H2O
were right.
has 2 oxygen. O2 has 1 mole.
Yes.
One
While
to two
O
ratio?
has 2.
It is. It is a
Yeah.
1 mole oxygen to 2 mole water ratio.
Good.
There's no
I
way.
guess I should prepare the wheel of
No
fun.
way. So, that's
Wheel of candy rewards.
Johnny, what did you get?
I do find it great that it remembers from day
What
to
did
day.
you divide by two?
This is period 5.
Because of that right there, what were you doing?
Connor. Connor. What'd you get?
yeah, that's what we got.
How'd you get 5.6?
Oh, you didn't divide by 2.
Why would you do that? Where'd you get?
Right?
Eli. Right. Eli, what did you get? How many moles of oxygen am I going to need?
2.8.
2.8. I like it. So let's see if your work matches my work. So I got 5.6 moles of H2O. Nothing goes in that box. The ratio tells me for every 2 moles of H2O, I'm going to make 1 mole of O2, and I'm done. So this just becomes 5.6 divided by 2, which is 2.8 moles of O2.
Oh, I forgot that oxygen can only be shown as 2.
O2?
Yeah.
Incoming candy.
I got 5.6. So that was close.
All right. So if you're with me and Eli, give me a thumbs up. If you have any questions, wave your hand around. Richard, what do you got? It's the coefficients in the balanced chemical equation. So 2 moles of water makes 2 moles of hydrogen and 1 mole of O2. So it's always going to be the ratio will always be the ratio of the coefficients. What we've been calling the mole ratio. Other questions?
Wait, so if it was 2, 3, 1, would it be 1 to 3 or something?
If it was 2, 3, 1, it would be still 2 to 1 because the hydrogen is not in this exercise. Other questions? All right, this one's for you again. Here we go. Calculate the moles of water created when 3.6 moles of aluminum hydroxide, that's aluminum hydroxide, reacted with excess hydroiodic acid. So work this one out.
Hydroiodic.
Hydroiodic.
Oh,
Yep, hydroiodic.
I eat it.
We have hydrochloric.
Whoa.
I think this might be the tallest thing I've ever printed.
So it's not a 1 to 2 ratio there. It's a.
It is not.
Wait,
It's
so
a
what's the aluminum hydroxide?
me.
Yeah. What's the aluminum hydroxide? Is that a 1?
It is. There's nothing there, so it's a 1, and the water hits a 3.
Let me make sure here. You want a red
What's hydrogen? 1.
I think it was pretty good, gas.
We'll say it's 1.
And 1 is good.
Oxygen 16.
It is.
It's always 16.
16.0.
No. 3.6 sales.
Since my Echo clock stopped working, I got a new timer over there.
Whoa.
I can say, Alexa, set timer 1 minute. Watch this.
Sure.
Alexa, set timer 1 minute.
1 minute. Starting now.
Oop, there it goes. That's cool. Yeah. So it was a lot cooler on the Echo wall clock, and I haven't entirely given up on it. But I figured until I figure out why it's not working properly. It keeps losing its Bluetooth connection. Yeah. Okay, one more minute.
I just did it.
What'd you get, Amy? So that's 1.2?
Well, yeah, it's 3 more because it says so this will be a 3. And that is
Multiplying it by the same number and then dividing it by that number is gonna get you the same product
okay.
every
Is
single
because there's already 3 figures and nothing right here.
time. God.
That answer's not 194. I'm telling you that right now.
Oh, yeah.
And don't
10 seconds. I did it.
Yeah.
Now 6 seconds. Now 4 seconds. Now 3 seconds.
You think I would probably win?
What?
You think I would probably win?
Maybe.
Alexa, stop.
That's just how they got it.
That's not the answer.
Wow.
You're not here. You
Well,
don't
when's
get to answer
Gianni?
a question.
I think Gianni can do that.
What?
Gianni can do it.
They're best friends.
No candy for you because you're not here. Wow, Mason. All right, so give me your answer and then we'll work through it. 1.2 moles? 1.2 moles of HOH. You guys, pay attention, please. Please pay attention. Okay, so we are starting with 3.6 moles of ALOH quantity 3, right? 3.6 moles of aluminum hydroxide. Okay. Make our box. Make our T-chart. And we're going to bring down our moles of aluminum hydroxide. Since our moles of aluminum hydroxide is in the top, we're going to put it down below, and we're going to convert to moles of HOH. What is the ratio of aluminum hydroxide to water? 1 to 3.
Yes.
The 3 is with the water. So for those who've been like, you always multiply, no. You don't always multiply, you always divide. This is 3.6 multiplied by 3, or 10.8 moles of HOH. How'd you do?
I did it right.
We actually had a
I was actually so disappointed.
We're just smart guys.
I have no idea what you just said. Dude,
Why isn't it water?
because you need to cancel out the units in the labels. So if we're starting with aluminum hydroxide up here, it needs to be aluminum hydroxide down here.
So you got one.
Okay. Do you want to do one more or move on to a limiting reaction exercise?
One more.
Uno mas. Here we go. How many moles of zinc metal would be required to completely react with 0.456 moles of hydrochloric acid? That's hydrochloric acid, that's our zinc metal. So work this one through.
So it's the first one and the second one we're doing,
Yeah, whoa, whoa, whoa.
Oh, yes, you become with yes.
Whoa, whoa.
Alexa, set timer 3 minutes.
3 minutes. Starting now.
I know you love me. I know you care.
That is unfortunate. How many?
What is hydrochloric acid? Is that the 2HCl?
HCl.
You stop saying that.
No, you're good. You're good. Where's your paper, Dennis? He's a freshman. Bad idea. I know what goes on in your head. You don't want to use your head.
I don't think you do know what it's dangerous.
Even though it
That's
is
a good point.
that's how you make
Lost.
yeah.
Yes.
So where would 0.46 go?
That's what you're starting with.
So you start, okay.
You're 0.46 moles of hydrochloric acid. Sorry.
So put that in. Put that in there.
What is mole?
Shut up.
Put that
Half of the thing on the map.
Zinc. What is zinc metal?
CN.
It's up there. It's,
Would be required to completely react. One is needed for two.
Can it be a decimal?
Absolutely. Yeah, again, molecules need to be whole numbers, but moles can be fractions just fine. Fraction, decimals, whatever it can be.
I don't get that.
Because a molecule is a single unit, but a mole is 6 billion of them. 6 times 10 to the 23rd of them.
So like,
Dimitri, you got decimal? You got decimal?
then what's a molecule? Sorry.
A molecule is a single unit of the atoms bound together.
So
You
that
cannot have
would
a, I'm sorry,
be, that would be the NCL too. Or is that the mole?
they're both molecules.
Oh.
So molecule is a single unit and mole is a whole bunch. Under a minute.
It's every time it's always one more.
Not every time.
No, so that means
If the ratio is 2 to 3, then it would be 2.
I kind of do that's silly.
The number is
Yeah, no.
Bro, you just explained this.
I
I'm watching YouTube.
No, I was not. I was not.
Yes, I think so.
Let's go.
Oh.
Yeah, it's, I feel like it's.
Just compare.
Because that's what we're doing.
Next time, pay attention.
I did it.
Try to get me to pay attention.
I did it.
Full answer.
That's kind of inappropriate.
Yeah, that's what
Yeah,
you're
yeah.
It's kind of weird for us to talk like that.
Yes.
It's on here.
Can I go?
I didn't even mark the accent. Alexa, stop.
Perfect.
I swear to God.
How many
decimal points do we want? Is it
What is your answer?
how many decimal points is it to again?
Let's use 3.
Is it 0.228?
0.228. I think it is.
That's actually
So,
4.
again, here we go, guys. We're going to look at 0.46, 456?
Yeah.
0.456 moles of HCl. Since moles of HCl is up top, we got to bring it down. Moles HCl. And we're going to convert to moles of zinc. And the ratio is for every 1 zinc, you got 2 HCl's. And that's going to be 0.456 divided by 2, which sounds like 0.228 moles of zinc.
Oh my goodness.
God
Question, Hannah.
God bless.
So if like the moles of zinc, like let's say the ratio is 2 to 3, so would you do 0.456
Thank
times 3 divided by 2?
Yes. Okay. We're going to do one limiting reaction exercise. This is for you to see how you were paying attention.
Yes, sir.
So our reaction is 2 sodiums plus a single chlorine makes 2 NaCl.
Yeah.
So my question for you is this. If, you ready?
Yeah.
We need 3 things. We need the number of moles of product, the limiting reactant, and how much of the excess is there. So we're going to have 3 moles of sodium and 2 moles of chlorine. Which one's the limiting reactant? How much product do you make? And how much excess is left over? Go for it. I'm going to leave that up there as a guide.
Okay. Wait, what do you?
Progress reports tomorrow. I remember.
Wait, Mr. Byers.
Yes.
Does that mean I have to redo my test by tomorrow?
If you want it included in the progress report.
It doesn't really
2
matter.
NaCl.
It depends on how much your parents made.
I'm
Some
sorry.
minutes that you do it.
How do you think that should be taken test by tomorrow?
Yeah.
The amount of chlorine is half the
I don't think I can.
Oh, you're right.
No, how do you recommend that you should be taking test?
So there's one.
Guys, I highly recommend you get to work.
I think
Be an active participant in your learning. You are not.
So 2 and 8 will be at the bottom.
There's one extra.
Stop.
Right?
Hold on.
You're going to make 2 T-charts. One's going to start with 3 moles of Na, and one's going to start with 2 moles of Cl. And they're both going to go to NaCl.
You should need to get a food job on, you know?
I'm not saying that.
Alexa, stop.
What is it? 3 moles of NaCl.
Yes, we will. Then
What do you mean 1.5?
you divide that. Oh, never mind. You multiply that times.
So, 1 mole.
Yeah.
Do they have to be complete number? Like, you can't have a decimal.
But
You totally can. Because we are talking about moles, not molecules. A molecule is a single unit. A mole is a whole bunch. Think of moles as like billions. But instead of billions, it's 6 times 10 to the 23rd.
I think I did it correctly.
I think I'm doing it wrong.
I guess we're gonna find out.
This is how I.
I guess we'll
You are.
find out.
Yeah, you did.
It is
Question.
Just one.
Yeah, everything goes down to 1.
Yes.
Is it 1.5 and 1?
I think I did it wrong.
There's 3 answers. There is how much you make, what is the limiting reactant, excess reactant, and how much excess is left over.
So how much is left over?
I'm going to start my work over here because we only have 3 minutes left.
Because I think this is how it goes.
Yes.
Oh, you already know that. Yeah.
That's what I'm telling you, man.
Oh, no, you didn't. Yeah, that's stupid.
1 NaCl and then 2 for every 2.
I was stupid. I was stupid. Oh, I know. I was just more like that. I was stupid. Oh, yeah, you the 2 from the NaCl. Yeah, we should have.
Okay, so.
Oh, we're trying to make one.
Dude. Oh, no, no, no.
Yeah, why's up?
So if you got to this point, you did 2 T-charts, and you found out that if sodium was the limiting reactant, you would make 3 moles of sodium chloride. If chlorine was the limiting reactant, you would make 4 moles of sodium chloride. So which one's the limiting?
The sodium.
The sodium's limiting,
Okay.
that makes the chlorine excess, and this is how much you make.
Yeah.
Now, once you know how much you make, you do a 3rd T-chart to figure out how much of the excess you used. Connor.
Is the lowest number always going to be the limiting?
Very never.
Huh?
Very never. The lowest number will only be the limiting okay, so the lowest amount made, are you talking about the lowest amount made or the lowest in the exercise?
The lowest amount made.
Oh, then very always. Yeah. So the lowest amount made will always be the limiting reactant. Will always be the product made from the limiting reactant.
Yeah.
Okay. So now that we know which one's the limiting reactant, we say, all right, I made 3 moles of NaCl. The exercise tells me for every 2 moles of NaCl, I required 1 mole of chlorine, which means I used 1.5 moles of chlorine of my available 2, so I have 0.5 moles chlorine excess. Yes.
I got that by doing 1 mole instead of 2 moles and 1 mole for the CO2 and NA.
Yeah, that's exactly.